All right, so I'm going to get started 1 minute early so that all of our speakers have the full amount of time. My name is Maas. I'm a research scientist at Google DeepMind, and I'm going to be chairing session 11B, which is about scheduling. Our first speaker is Zizhao Mo. He's a third-year PhD student from the University of Macau. His research interests include scheduling and resource management for deep learning training jobs and LLM serving for distributed systems perspective as well. Take it away.
Okay. Hi, everyone. I'm honored to be here to introduce our work, Heet, accelerating elastic training of deep learning training jobs in the deep learning clusters. Because of the rapid development of GPU technologies, GPU heterogeneity has already become common in today's deep learning clusters. As an example, there is 8 GPU types in Google Cloud Platform. In general, 2 types of heterogeneities are found in today's deep learning clusters, the communication and computation. For the computation, as listed in the table, we can see that A10 GPU has nearly 2 times higher computational power than T4 GPU in FP16 computation, while the A10 GPU has nearly 4 times computation power than T4 in FP32 computation. For the communication, some GPU can only be interconnected by the PCIe channel, which transfer tens of gigabytes per second. While some advanced GPU can interconnect it by the NVLink, which transfer up to 900 gigabytes per second. Computation heterogeneity has a great impact on the deep learning training. The primary reason is that architectural differences influence the computation intensity of deep learning training. As an example, deep learning training jobs differ in their multi-layer perceptron size, the hidden dimension size, and the convolution size. These differences lead to diverse benefit from the computation power and eventually leads to diverse acceleration effect. As presented in the below figure, deep learning training jobs are accelerated from 1.7 times to 2.9 times given A10 GPU. Communication heterogeneity also has great impact on the deep learning training, since the architectural differences influence the communication intensity of deep learning jobs. To be specific, deep learning training jobs that differ in the size of gradient to be synchronized at each iteration and the overlap conditions of computation and communication in the backward phase. These differences lead to diverse benefit from the communication channel and eventually leads to diverse acceleration similarly. As shown in the figure, deep learning training jobs are accelerated from nearly no improvement to up to 4 times given an NVLink channel. As elastic training becomes a common training paradigm, the scaling efficiency turns into an important concern since it characterizes the speed up given more GPU workers. The scaling efficiency is determined by the synergy of communication and computation. As an example, given more GPU workers to a distributed training job, its computation time decreases with the workload distributed to each worker, but its communication time will improve with the size of gradient synchronization group. As such, the high-end GPUs can diversely influence the scaling efficiency of jobs. As we observe, high-end GPUs in computation can lead to low scaling efficiency, but high-end GPUs in communication can always lead to higher scaling efficiency. So here comes an intricate trade-off. To improve the scaling efficiency, the ResNet prefer T4 GPU, but the VGG will prefer the V100 GPU. In addition to the scaling efficiency, scheduling efficiency is also important to the overall scheduling performance, since different job arrangement may lead to totally different scheduling performance. To reduce the overall job completion time, a typical strategy in scheduling domain is the SRSF, which means shortest remaining service time first. This strategy always schedule the short job first to avoid the convoy effect. However, this simple strategy cannot be directly adapted to the elastic chaining in heterogeneous deep learning clusters, since the job length is determined by the number of workers assigned to them and the GPU types assigned to them. We demonstrate this is an NP-hard problem in our paper. Moreover, implementing an efficient scheduling system for deep learning training jobs in a heterogeneous deep learning cluster is very challenging. The first challenge is the large profiling space for the elastic deep learning training jobs. To obtain the full throughput information, we have to navigate all the GPU types, all the job types, and all the possible number of workers for each job. Another challenge is that we have to conduct an intricate trade-off between the scaling and scheduling efficiency. Merely improving the scaling efficiency requires us to allocate fewer jobs to fewer workers to each job. However, this can ignore the job length information and lead to bad scheduling efficiency. On the other hand, merely improving the scheduling efficiency requires us to allocate more high-end GPUs to the short jobs. However, this can lead to the bad scaling efficiency since few jobs are simultaneously scheduled at the same time. As shown in the right figure, we demonstrate that only by balancing between the scaling and scheduling efficiency can we have satisfactory scheduling performance. To address these problems, we propose our solution Heet. Heet consists of three main modules: the profiler with collaborative filter-based techniques to minimize the profiling overhead, an orchestrator module, which conducts bipartite matching and trading process to optimize their allocation, and a placement optimizer, which reduces the cross-network placement for higher training throughput. We are going to introduce the profiling module first. We call it as a 3D profiling since it incorporates the effective profiling for job types, GPU types, and the number of workers. First, we detect if there is this history jobs with high similarity. If so, we populate the throughput information from the history data. Otherwise, we apply the PQ decomposition from the throughput information already profiled. By doing so, we can offer low profiling overhead and high profiling accuracy. Then we are going to introduce the orchestrator module. But before talking about the technical details, we first have a look at some cluster level orchestration restrictions. The first restriction is that the juggling effect is harmful to training. If we give a high-end GPU and a low-end GPU to a distributed training job simultaneously, the high-end GPU will wait for the low-end GPU due to periodic gradient synchronization. So the power of high-end GPU will waste. The second restriction is that the cross network placement is not recommended, since the large volume of gradient synchronization is susceptible to slow network. In orchestrator module, we propose a scheduling price design. Specifically, it is the job length given an allocation divided by the gap its gap to the perfect scaling. This design balance between the scaling and the scheduling efficiency. Moreover, we propose a resource partitioning scheme where GPUs are allocated to jobs by groups. GPU grouped together are of the same type, and the group arrangement can minimize the cross-network placement. Given the scheduling price design and the resource partitioning, we then apply the mean cost bipartite matching to find out the allocation of GPU group to the deep learning training jobs. However, the fixed size partition is not flexible enough and may produce suboptimal allocation. So we introduce a second phase improvement, the opportunistic trading. In principle, we piggyback staff job from the workers from the scaling inefficient jobs. As shown in the figure, reducing one worker from scaling inefficient job has little impact, but this worker can be used to accelerate the completion time of the staffed jobs. We demonstrate the performance of Heet in a cluster consisting of 8 T4 GPU, 8 A10 GPUs, and 8 V100 GPUs. First, Heet presents high accuracy in 2 profiling phases and incur low system overhead, profiling overhead. Second, from a macroscopic view, Heet reduces the JCT and mid-span effectively, no matter the job length is given or not. Third, from a microscopic evaluation, we also demonstrate a better performance of Heet from the scaling efficiency and the blocking index. Lastly, Heet can achieve low system overhead and only up to 3% of time are spent on the training reconfiguration. This concludes our work. Thanks for your listening.
All right. Do we have any questions? All right, I can ask one. So one of the things you mentioned, first of all, really great talk. I like the multi-step process a lot.
Thank you.
Is there, you mentioned at the beginning that this is an NP-hard problem. Have you tried putting this problem into a solver and seeing how far the solver gets, or whether the solver is able to find an approximate solution?
Yes, as we use the NetworkX library to solve the network problem, the bipartite matching, we already demonstrate that Heet can solve the problem from a large scale, such as thousands of jobs in few seconds. So, but however, due to the space limit, we cannot put all the experiment result in this PowerPoint. So yes, we did it. We did it.
Thank you.
Thank you.
Do we have any other questions? So I think we have time for one more. So you're basically looking at the dimension of splitting the work into different numbers of GPUs.
Yes.
Are there other dynamic properties of the workload that you could apply your work to? Like, for example, are there different ways you could configure the workload or compile the workload that would create a similar design space that you could explore?
Do you mean the type of deep learning training jobs, or
Yeah, for example, or just some way you have the same job and you can run it in different ways.
Yes, this is already incorporated in our profiling. Since for example, a common task is the hyperparameter tuning. In this case, some jobs are already have high similarity. If we have already profiled for some of them, and the other of them can leverage the historic jobs to help them to populate the training super information. So this is incorporated in our design.
As the collaborative filtering can capture other properties as well.
Yes, yes.
Very nice. Thank you so much. Let's
thank
thank
you
the
very
speaker
much.
once again. All right, our second speaker is Zhihong Luo. He's a PhD student in computer science at the University of California, Berkeley, advised by Professor Scott Shenker and Professor Sylvia Ratnasamy. He's primarily interested in networking and operating systems. Prior to coming to Berkeley, he received his master's degree from MIT and bachelor's degree from the University of Michigan Ann Arbor and Shanghai Jiaotong University.
Hello, everyone. Thank you for being here. My name is Zhihong. I'm a PhD student at UC Berkeley. Today, I'm excited to tell you about our work, efficient microsecond-scale blind scheduling with tiny quanta. This is a joint work with my colleagues Sam, Dev, Emmanuel, Amy, Sylvia, and Scott. To efficiently service microsecond-scale requests under latency SLOs, one needs to achieve both low tail latency and high throughput. We focus on blind scheduling, where achieving low tail latency requires frequent preemptions. This is because header-line blockings, where short jobs are blocked behind long jobs for excessive amount of time, cause significantly increased latency of the short jobs. And therefore, to minimize header-line blockings, blind scheduler typically adopts some notion of processor sharing, where there is some quantum of service allocated to each job before we preempt it and move on to the next one. And it's well known that in order to guarantee low tail latency, one needs quanta sizes sufficiently smaller than the short jobs in a workload. In this work, we decided to push to the extreme and end to schedule with quanta size as small as 1 microsecond, and call the resulting system TQ, which stands for tiny quanta. While using tiny quanta is beneficial for low tail latency, sustaining high throughput with tiny quanta leads to 3 challenges, including switching overhead, scalable scheduling, and cache pollutions. In TQ, we overcome these challenges with a novel combination of 2 mechanisms, force multitasking and 2-level scheduling. In this talk, I'll briefly describe the high-level insight behind this mechanism as well as our design for them. For switching overhead, using hardware interrupt to preempt worker call has an overhead of a few microseconds. Even with optimized interrupt system enabled by non-standard virtualization feature, Shinjuku, a prior microsecond scale preemptive scheduling system still have an interrupt overhead of about 1 microsecond. Such an overhead is too expensive and cause substantial throughput degradation when we try to operate under tiny quanta, such as a quanta less than 1 microsecond. Therefore, to work with tiny quanta, we turn to using coroutines, which has a much lower switching cost at the order of magnitude of tens of nanoseconds. However, the common use of coroutines require manual insertions of yielding points from the developers, which is both burdensome and error-prone in our case, because we need to ensure that each job will yield a core every couple of microseconds. To fix this issue, we propose force multitasking, where we essentially have the compiler instrument the jobs with many probes, which will check and make sure to call the U function every quantum. With force multitasking, the goal is we take advantage of the low switching cost of coroutine without burdening the developers. However, the key challenge is now, how can we introduce minimal probing overhead while ensuring reasonable timing accuracy? The reason is that if you spend too many cycles probing and trying to figure out the right timing to yield, you will end up again with expensive multitasking mechanisms. Prior compiler instrumentation work, you adopt an instruction counter-based approach. In this approach, the compiler essentially maintains an instruction counter with probes. and each probe will increment the instruction counter by a value that is determined at compile time. And then at runtime, you basically translate the target quantum into a target instruction count, and the probe will call a U function if the value of the instruction counter is larger than the target instruction count. However, instruction counter-based approach introduced significant probing overhead. This is because even though each individual probe is cheap, too many probes need to be inserted in order to maintain the correctness of the instruction counter. For example, for RuxDB GET operations, instrumented instruction counter-based probes leads to a 60% slowdown of the work. Moreover, instruction counter-based approach is fundamentally inaccurate because of the translation from cycles to instruction counts. To fix this, in TQ, we adopt a different approach based on using a physical clock. Essentially, instead of using an instruction count, each probe will simply read from a hardware cycle counter and yield if enough cycle has passed since the previous U point. At first glance, using a physical clock seems to worsen the overhead issue because now a probe is much more expensive. However, unlike the instruction counter-based approach, where probes need to be inserted frequently to ensure the guarantee the correctness of the counter, physical clock-based probes can be placed in any location of the program and they can function correctly there. Because of this, we can place the probes much further apart, which result in much fewer probes and overall a reduced probing overhead. Moreover, because reading from a physical clock is inherently more accurate, you will be able to achieve better timing accuracy despite a sparser placement. In summary, TQ's physical clock-based instrumentation techniques allow us to do forced multitasking with much lower overhead as well as good timing accuracy. Besides switching overhead, prior systems also suffer from limited scalability and cache pollution due to the use of centralized scheduling. This is because the dispatcher is responsible for scheduling all the quanta of all the worker cores. As a result, when we reduce the quanta size, the dispatcher will become a throughput bottleneck. Moreover, because you schedule the quanta of a job among multiple cores, this leads to more cache pollution, and these additional cache misses can cause performance degradation. To fix this, we propose a two-level scheduling framework. The key observation here is simple. Is that with forced multitasking, job multiplexing can happen within each core locally without requiring any external assistance. As a result, it's possible to have the dispatcher perform a minimal set of work while still ensuring good scheduling performance. Specifically, with two-level scheduling, the dispatcher is responsible only for job level load balancing, and quantum scheduling is offloaded completely to each individual worker core. From a high level, it's clear that this is more scalable because the load of the dispatcher is significantly reduced, and it remains constant when you change the quantum sizes. Moreover, this also brings advantage in terms of cache because now that a job resides in the same core throughout its executions, the cache pollution can be contained, which leads to less cache misses and less performance degradations. Specifically, with two-level scheduling, now TQ works like this. After receiving an incoming request from the NIC, the dispatcher simply forwards the request to one of the worker core following some load balancing policy. And then after that, worker cores will take care of preemptively scheduling the quanta of all its assigned job by themselves without any external interrupt. And after the worker core are done with its job, it will directly send back the response to the NIC without going through the dispatcher. And the dispatcher simply keep track of the load of each worker core in order to perform high quality load balancing. In TQ, we adopt JSQ, join the shortest queue, as a load balancing policy, which means that the worker core with the smallest number of jobs in the queue is going to be picked. JSQ is a blind policy that can be efficiently implemented, and moreover, the combination of JSQ and process sharing has been proved to be near optimal for the average job latency. The tail performance of the JSQ-PS combination haven't been studied in theoretical work, but we empirically found that the tie-breaking policy, which determines which worker core to pick when they all have the smallest number of jobs in the queue, actually matter for the tail performance. And in TQ, we propose a tie-breaking policy called MSQ, which essentially pick the worker core that have serviced the most number of quanta of its jobs. And then in experiment, it's shown to provide good tail latency. To summarize, building on top and enabled by forced multitasking, two-level scheduling is much more scalable and cache-friendly compared with the traditional centralized scheduling framework. We implemented and extensively evaluated TQ, and then here is key takeaways from the evaluations. First, in terms of the support of a tiny quanta, TQ can sustain high throughput with quanta as small as 1 microsecond. In terms of end-to-end performance, TQ is able to achieve low tail latency while sustaining much higher throughput than prior blind scheduling systems like Shinjuku and Caledon. With a performance breakdown, we show that both mechanisms of TQ, force multitasking and two-level scheduling, plays a vital role in TQ's superior performance. And with the cache evaluation, we show that frequent preemption is unlikely to cause notable performance degradation in TQ, thanks to the use of two-level scheduling. Lastly, we perform a wide range of micro-benchmarks, which demonstrate that both two-level scheduling and force multitasking fulfill a desired property of them. For instance, force multitasking is able to achieve very accurate preemption timing with very low probing overhead. More details of the evaluation setup and the results could be found in the paper. To conclude, in TQ, we enable efficient and scalable blind scheduling with tiny quanta, which allow it to achieve both low tail latency as well as high throughput. TQ delivered this with a novel combination of two mechanisms, force multitasking and two-level scheduling. And with an extensive evaluation, we show that TQ is able to substantially outperform prior blind scheduling systems in terms of tail latency as well as end-to-end throughput. With this, I'm ready to wrap up my talk and answer any question that you may have. Thank you.
If I have two jobs, one takes an hour and the other takes an hour, by doing your context switching every microsecond, do I improve tail latency?
No, because what you refer to is called a low dispersion kind of like scenario. Essentially,
so my question is, you say it as if it's a fact, but it isn't. The fact that you context switch on a very fine granularity doesn't mean you improve tail latency.
Yes, to be exact, it improves tail latency and it's proven to be theoretical optimal for high dispersion scenario, which means that there you have something that's really short and something that's really long. Or put it differently, it helps when there's a significant head of line blockings. But in the case where the jobs are similar lengths, first come first serve is both cheap and is already optimal.
But I'm assuming, I didn't read your paper, but I'm assuming that you're talking about like the network function sort of a scenario, right? It's a network function.
An example scenario where there's high dispersion is, for example, like if you have a key value store and you have a get and a scan. And the scan can be like 1,000 times longer than the get. And in that case, head of line blocking is really severe and preemption matters a lot. But,
so I agree with you that in that case, you'll improve. But if you have only scans, then you're lowering the throughput and...
Yeah, right. When there's little dispersion, first come first serve work great. And then both in terms of tail latency as well as throughput. That's been proven, and you are definitely right on that. Thank you.
Hello, thank you for the great talk. Ayan from EPFL. So I have two questions. The first question is, do you have any impact on average latency?
Do you want to finish your second? The average latency, we measure it, but we didn't show it in the paper. I would not, on the top of my head, I feel like I remember it was similar improvement in terms of, because the point is that you can sustain a low latency for higher throughput. And I think that's the same even with mean or other percentile of the latency. But in the paper, we mostly focus on the tail. Yes.
Okay. And my second question is a bit related to what the previous question was. I understand that if the head of the queue is blocking, then all the previous requests are also being blocked. But like, why do we need to go down to like 1 microsecond scales? Can we not do something?
That's a good point. Essentially, as I say, this is kind of like a push to the limit, see how far we can go kind of attempt. But if you want to say on the practical terms, you will 1 microsecond or like a tiny microsecond, it's beneficial when your short job is on a few microseconds. Basically, if your short jobs are like hundreds of microseconds, you don't need quanta size decimal. So that's, yeah, to answer your question. But this is kind of like also like push to the limit and see how low can we actually get and still deliver pretty good performance. And together, but there are some key value store. For example, if you do a get in a relatively small in-memory key value store, it actually lasts like less than 1 microsecond, 1 or 2 microseconds, in which case a quanta size of 1 microsecond or 2 microseconds will help a lot. So to answer your question, yes, it depends on workloads. If the shop jobs are like hundreds or tens of microseconds, then you probably do not need to go down to 1 or 2 microseconds for the quanta size.
Okay, thank you very much.
Thank you.
Hi, thank you for your talk. And so you mentioned about physical clocks and physical clock probing. What is the actual implementation of that probing? Are you using a polling approach, or you have some sort of synchronization between clocks to make sure you have a unique notion of time between those workers?
We will basically use in x86 use RDTSC to kind of like as the ground truth of like how many how many cycles it elapsed since the last time I checked. And then the key takeaway here was that because I don't need to maintain a counter. I can place them as far apart as possible. I have more flexibility in the placement, so I can place them much sparser. Even though each one of them, it was surprising to us, but each one of them is actually more expensive. But because you place so much further apart, the resulting overhead is actually like half of the previous approach when you need to put the instruction count, maintain the instruction counter, but you need to place them much more densely. So that was the main takeaway from that part of the TQ. Yeah.
Okay, thank you so much.
Thank you.
Right, I think our next talk is virtual. All right. Our next speaker is Seyedali Jokar Jandaghi. They're a PhD student at the University of Toronto, where they've been focusing on designing techniques to improve efficiency in cloud public systems. Research focus on managing instances with dynamic resource assignment policies by leveraging insights from extensive dataset analysis, and open to opportunities in industry and academia.
Hello, my name is Ali, and I'm excited to present our collaborative research work, Audible, which is a new scheduler designed for burstable virtual machines. This work is a joint effort between Microsoft Research and Universities of Toronto and Michigan. Here is how a burstable virtual machine works. Unlike traditional VMs, which have fixed CPU access, burstable VMs operate with dynamic CPU access. As you can see in the figure, this is an example of a CPU usage for a burstable VM over time. This graph shows the credits for the burstable VM over time. I'm going to go over 3 phases for this example of the burstable VM CPU usage. A phase we call it baseline performance, credit accumulation, and burst phase. Each burstable VM is configured with a baseline value, guaranteeing a minimum level of CPU access at all times. In the top graph, that's shown by dotted red line. When the CPU usage is below the dotted red line, or baseline value, it can start collecting some credits. Later, when it wants to burst over the baseline, it can use those credits that it had been collecting before in order to go above the baseline value. If it doesn't have any credit, the usage will be capped at baseline value. Think of this workload running in a regular VM. The user had to pick a large regular VM that can accommodate those bursts. But in the case of burstable VMs, that's not the case. So this is a unique characteristic to burstable VMs, and it allows them to co-locate on a server and share CPUs together. So we want to look at the objective that the scheduler should take into account for placing them on a server. Suppose we have a queue of burstable VMs that the scheduler needs to place on servers. Each one of these burstable VMs have their unique baseline value, and the values varies from as little as 0.05 CPU core to a large value almost around 3 CPU cores. The scheduler should make sure to pack burstable VMs as tight as possible. This is because it can utilize the server CPU more efficiently this way. But we should keep in mind that when we have multiple burstable VMs sharing a CPU, there is a chance that they may burst simultaneously. And as a result, there's a chance that resource shortage happens. Service level objectives puts a boundary on the acceptable resource shortage. We want our scheduler to meet this strict resource shortage threshold. Let's look at the current scheduler in practice. Azure reserves 2 times the baseline for each one of the burstable VMs and then place them on the server. We have seen that this method results in poor server utilization, just around 10%. So given that, we're going to summarize all the different scheduling techniques in this summary table. And we're going to look at how well they're doing in terms of the objectives for the scheduler that we want for burstable VMs. So far, we've seen the current scheduler in Azure, which is allocating 2 times the baseline. It results in low utilization, although it doesn't encounter any situation with unacceptable resource shortages. Next, we looked into another common scheduling method that has been used in for other type of cloud instances, such as containers. It's called central limit theorem, or in short, CLT. What it suggests is that the aggregate usage of a set of co-located virtual machines on a server form a Gaussian distribution. We have borrowed this idea, adapted it to burstable virtual machines, and we have seen that it actually achieves high utilization. But unfortunately, it encounters severe resource shortages in some scenarios. Let me show you a graph that shows the empirical distribution of a server hosting burstable VMs and what actually CLT assumes the distribution should look like. As you can see, the empirical distribution is a skewed distribution, while the CLT assumes it's a symmetrical Gaussian distribution. So that's why this method is not able to meet the strict resource shortage threshold we're aiming at. But we're digging into what is the reason for this skewness in the empirical distribution. And we have found that large burstable VMs, even though they're rare, but because they have large spikes, can cause very large usages on a server and create that bump at the tail. Getting back to our summary table, the utilization of the central limit theorem is quite high, and that's good, but resource shortages is not acceptable. Now I'm excited to share with you a new scheduling technique, which we call it Audible. In order to design the Audible, we first looked into 3 datasets from Microsoft Azure. We analyzed the datasets, including millions of records of regular VMs and burstable VM workloads. Azure collects telemetry information, including the burstable virtual machine CPU demands and the server CPU demands. We looked into both regular VM workloads and burstable VM workloads in order to find the distinctive features of burstable virtual machine workloads that set them apart from regular VMs. We have seen that burstable virtual machines show higher CPU demand in their early stages of their lifetime. And we have also figured out that the skewness in the CPU usage of a server hosting burstable VMs is higher. And this is because the workloads of the burstable VMs are more bursty. Given those insights, we were able to create 2 sets of tables or inputs that Audible will be using in order to operate. The first one includes a conservative CPU demand probability for each one of the 10 unique burstable VM configurations. In Azure, there are only 10 VM configurations. And by looking into the historical data, we were able to create a conservative CPU demand probability for each one of the configurations. This is necessary because when a burstable VM arrives to the system, we have no information about it other than its configuration. The other table was built based on the empirical server usage. This information is available by Azure collecting telemetry. And for each one of the servers, we were able to create a CPU demand probability based on what had been observed. Let's see how these 2 tables are being used being used in the case of Audible. Upon arriving at burstable VM with configuration X, Audible will fetch the conservative CPU demand probability of this configuration from the yellow table, which has all the CPU demand profiles for different burstable VM configurations. And then when it wants to assess whether if this burstable VM can be placed on server Y, it fetched the observed CPU demand probability of that server from blue table, which contains the CPU demand probabilities for all the servers. This is an example of what the CPU demand probability for a server may look like. It has a tail that goes above the capacity of the server, and that area under the tail shows the resource shortage probability. So Audible also has the burstable VM CPU demand probability coming from the configuration of the burstable VM. What it needs to do is to create the combined CPU demand probability, given that this burstable VM is getting placed on this server. It creates the joint probability of these two distributions by convolving them, and the distribution looks like something like this. The resource shortage probability, or the area under the tail, now has changed. Audible should assess whether if this new resource shortage probability is still within the acceptable range or not, and based on that, either accept or deny the placement. We have seen that Audible achieves high utilization, almost around 55%, and more interestingly, it does not encounter any unacceptable resource shortages. In summary, Audible has the advantages we were looking for. It achieves high utilization, and it meets the resource shortages the resource shortage threshold that we were looking for. Here is a partial result of a set of extensive simulations that we've done. In this result, I'm showing you for the resource shortage threshold set to 0.5% and servers size set to 48 cores. As you can see, the 2x baseline, or reserving 2 times the baseline for each one of the burstable VMs, which is the current Azure scheduler, results in a poor utilization of the servers. CLT achieves high utilization, but it cannot meet the strict resource shortage threshold. And Audible can achieve high utilization, while also it meets the resource shortage threshold set by the service level objectives. So maybe the baseline method, or the 2x method, could have done better if we had a better choice of the oversubscription factor. Maybe if we have picked a smaller factor, such as 1 or 0.5x baseline, we could have done better. We took an Oracle approach, and we picked the best possible coefficient for oversubscribing CPU according to the baseline value of each burstable VM. We call that method oversubscription Oracle. Even in this case, the utilization of this method is not as good as Audible. We have tried Audible in different settings, with server sizes from 36 cores to 64 cores, and resource thresholds from 0.5% to 5%. In all scenarios, Audible outperforms other methods, and it always meets the strict resource shortage threshold. Let's recap our key contributions in this work. We've conducted the first detailed study of burstable virtual machines. We have identified inefficiencies in the current scheduling methods for burstable VMs, and we introduced Audible, a scheduler designed to place burstable VMs efficiently. Thank you.
All right, I believe we have the speaker online for questions.
Hello.
Can you hear us?
Hi.
All right, do we have any questions?
Hello, Zhihong from Berkeley. Great talk. Some questions here. First, 2 questions here. First one is regarding CLT. I may be missing some points, but usually CLT assumes that the variable are identical. So But in this case, as you say, some VMs are bigger than the other. I'm not sure whether it's appropriate to apply CLT in that context. And also, CLT usually work when N is pretty large. I wonder how many burstable VM actually fit in a single server, and whether that N is sufficiently large to justify the use of CLT. And the second question is, how do you imagine, because Audible, if I understand correctly, take a statistical approach. Do you think, how would you think if you can you apply it to like incompressible resources like memory, where if you go out of it, it's just like you're gonna run into a big problem? So what do you think of, can you do anything like that, statistical method for memory? And yeah, your thoughts on that. That's my two questions.
Yeah, thank you for the questions. As for your first question about CLT, you're right. The CLT assumes that the random variables are IID. And as you just mentioned, it also needs to make sure that no specific random variable has a large dominant variance. So we have, in our case, depending on the size of the server, we have many burstable VMs. It could be even up to 150 for large servers. But the thing is, when we looked into the distribution of them for burstable VMs, it was skewed. And even though they were IID, so we didn't pick any, they were independent, so they're the workloads in the burstable VMs. But because there was a dominant variance, it makes the CLT inapplicable to our scenario. So the reason that we picked CLT is because if you look at the research for small cloud instances, such as containers, it has been one of the methods that had been recently used. And for example, I'm referring to the Take It to the Limit paper. And we thought maybe this could be something that fit our problem too. But for the reason that I mentioned, it did not work. Your second question, if I pick it correctly, is whether if Audible is working with the memory over subscription as well. Did I pick up your question correctly, or was it a different question?
Thank you so much. Let's take the speaker once again. All right, and this brings us to our last talk, and which is also a virtual talk. Our last talk is by Cristiana, who's currently an engineer at DeepSeek AI focused on the infrastructure of pre-trained foundation models. He received his master's degree from Shanghai Jiaotong University in 2024, specializing in virtualization, learning under the supervision of Xiaomi. Before that, he received a B.Eng degree from Shanghai Jiaotong University in 2021.
Hi, I would like to present CPS, a cooperative hyper-virtualized scheduling framework for medical machines. Nowadays, virtual machine can be really large. AWS, Alibaba, Google Cloud, Azure, they'll provide virtual machine with around 100 virtual CPUs and even more. These virtual machines are deployed to medical machines like Intel Xeon and AMD EPYC. Naturally, we care about the scalability. Unfortunately, applications in the virtualized environment scales worse than that in the native environment. As you can see in the figure, the x-axis is the thread number, the y-axis is the normalized performance. The higher, the better. The native environment has the highest performance. The PV-SCAD is a KVM feature, with PV-SCAD enabled or not. The virtualization doesn't scale well as the thread number increases. Another problem comes from the medical machines is the complex deep memory hierarchy. The medical machine have different sockets, nodes, and cache groups. In one cache group, there are 2 to 6 physical cores sharing a single loss level cache within the NUMA node. The threads running on these cores have higher communication throughput than those outside this cache group. We did an experiment. We run 4 threads accessing the same memory simultaneously. In our paper, we call these threads interactive threads. When the threads run in the same cache group, the throughput is 7.8 million operations per second. When we scatter the threads to different cache groups but still in the same NUMA node, the number is 4.76. When the threads scatter in the same socket, we get 4.45. When the threads in the different socket, we have 2.97. Therefore, if the threads running the virtual machine scatter physically far away from each other, they have to endure performance degradation. All of this performance problem can be reduced to runtime hypervisor internal state problem, the RHS. The RHS in our paper is the dynamic host information that helps guests to schedule, such as the cache group topology information and the CPU load degree information. However, in current implementation, guest is unable to see RHS, or they have to access the stale RHS. Therefore, they have to blindly make bad scheduler decisions. So we try to solve this problem by proposing a framework for many-core machines to expose runtime information to guest so that the guest scheduler can make smarter decisions. The overall architecture is as follows. First, the host scheduler passes dynamic scheduling and hardware information. And the backend and the frontend communicate together with organized data into a structured format, the refer table, which we will talk about it later. Finally, the guest query for the latest information and make smarter scheduler decision. The refer table consists two levels of blocks, the per virtual CPU level and virtual machine level, making it extendable to incorporate more internal information in the future. The virtual CPU stores the index to the actual data in the virtual machine level refer table. In the virtual machine level refer table, the data can be local or pointer to some global information that can be shared with other virtual machines. We have two use cases. The CPS payload, we try to expose host runtime physical CPU load degree information. And the CPS CG-SCAD, we expose runtime virtual CPU to cache group mapping information so that we can co-locate the interactive threads. Now we talk about the background of the first use case, the CPS payload. In current system, there are two schedule mechanisms, the hardware-assisted VM and the parallel virtualized VM. For example, we have 4 physical CPU cores, and we have 1 online virtual CPU and 3 preempted virtual CPUs. In current system, the task might schedule to a preempted virtual CPU, which means the task have to wait until the virtual CPU resume to be online. It will slow down the task performance. We call this design the HVM in our paper. KVM introduced PV-SCAD feature to mitigate this problem. The PV-SCAD only schedule tasks to online virtual CPU. We call this design the PVM in the paper. However, if multiple threads are to be scheduled, these threads have to crowd into limited number of online virtual CPUs, and it didn't fully utilize other physical core resources, causing load imbalance, and that's why application with PV-SCAD even sometimes perform worse than that without it. So we expose host load degree information to the guest. The virtual machine level refer table will store load degree pointer that point to the host CPU load degree information. Here is the design of the CPS payload after the information exposure. First, the backend updates the physical CPU core load degree information to the guest in the refer table, and it tells the guest kernel that some physical core is not busy, represented by the letter L. Then the guest kernel can enlarge the list of the candidates of the available virtual CPUs. Since the virtual CPU on the low load degree physical core can be rescheduled quickly, so the task running on it will be executed soon. Moreover, now that the number of available virtual CPU increases, it can also reduce the task crowd problem. Okay, this is the design of the CPS payload. Now we talk about the background of the second use case, CPS CG-SCAD. For example, initially, thread 0 and thread 1 are interactive threads, and they are in the same cache group. However, the dynamic virtual CPU migration separates thread 0 and thread 1 to different cache groups. Therefore, the collocation fails because of the virtual CPU migration. The virtual CPU migration to different physical core is common in the virtual machine. Therefore, it is hard to collocate the interactive threads. We try to solve the problem by proposing virtual CPU to cache group map information to guest. The VM level refer table will store the virtual CPU ID and cache group ID in its corresponding rows. So here's the design of the CPS Zizhao design. The thread 0 and thread 1 are interactive threads, and thread 0 is already running in virtual CPU 0, and the guest scheduler tries to select the virtual CPU for thread 1. The host will share the latest virtual CPU to guest mapping information. The mapping shows that the virtual CPU 0 is in cache group 0, virtual CPU 1, cache group 2, virtual CPU 9, cache group 0. At step 1, thread 1 will refer to the per thread group data structure. This data structure stores the thread distribution among cache groups, and it finds out that cache group 0 has the most number of other interactive threads. Therefore, hopefully, thread 1 should be scheduled to cache group 0. At step 2, thread 1 will refer to the per virtual machine data structure. This data structure stores the virtual CPU number and thread number of each cache group. This data structure keeps load balance between cache groups, and luckily, it will find that the cache group 0 still has some idle virtual CPU. Therefore, it will find the very idle virtual CPU in the cache group 0. Let's say it's the virtual CPU 9. At step 3, thread 1 would be scheduled to virtual CPU 9, and the interactive threads are successfully co-located together. So this is the design of the CPS Zizhao. We modify both the host Linux and guest Linux codes to build the framework infrastructure. And on top of the infrastructure, we build the CPS payload and the CPS Zizhao. CPS is evaluated on an ARM-based many-core server with 128 ARM physical cores, 256 GB memory, and 1.9 TB storage. Both guest and host kernel are open EULAR with Linux 5.10, and we use QEMU5. The CPS payload is evaluated on parsec benchmarks. In the figure, the x-axis is the benchmark applications, the y-axis is the performance improvement of the CPS payload compared to HVM and PVM. The higher, the better. We evaluated the benchmark on both under-committed scenario and over-committed scenario. The results shows that the CPS can improve the performance of parsec by 8% on average. Because CPS payload can squeeze the performance potential of these low-load physical cores, and it provides an effective way to allow these threads to be scheduled on preemptive virtual CPUs that can be quickly rescheduled to be online. Therefore, CPS payload is better than PVM and HVM. This figure shows the scalability analysis of CPS payload. The x-axis is the thread number. The y-axis is the execution time. The lower, the better. As the thread number goes, CPS payload performs better than HVM and PVM. PVM suffer from poor scalability due to small number of available virtual CPUs. HVM may blindly schedule tasks to a virtual CPU running on a busy physical core. CPS payload, on the contrary, can enlarge the number of available virtual CPUs and make sure to schedule tasks to a low load degree physical core. Therefore, it shows the best scalability. The CPS Zizhao is evaluated on FXmark benchmarks. In this figure, the x-axis is the benchmark application. The y-axis is the performance improvement of CPS Zizhao compared to the baseline. The higher, the better. The CPS can improve the performance of FXmark by around 100% on average, because it effectively co-locates the interactive threads into the same cache group. In conclusion, we analyzed 2 cases of RHS problems in large virtual machine on many core servers, and we present CPS, a hyper-virtualized scheduling framework to mitigate the RHS problem in virtualized environment. We propose 2 cases, the CPS payload and the CPS Zizhao, and we improve the parsec applications by around 80% on average, and we improve FXmark applications by around 100% on average. Thank you.
All right, so I believe we have the speaker for questions.
Yeah.
Can you hear us?
Yes.
Hey, thanks so much for joining. All right, do we have any questions? I can ask one. So quite a while ago, there used to be work on multi-level scheduling for coordinating the assignment of parallel workloads to cores, like Lyth out of UC Berkeley is a good example of that one. And I'm curious what you thought is how these techniques in kind of the virtualized environment may or may not compose with those kind of approaches to co-schedule, for example, multiple OpenMP workloads together to maximize the throughput.
So I assume the question is about this work, the differences between this work and some other scheduling technique like the co-scheduler.
Yeah, or just how can they be combined, for example?
How to be combined, for example. I think this work is most focused on the virtual CPU core selection, and I have seen other works like the ECS. They try to propose some workload on the scheduling on a single core. So I think that they can be combined together because we propose a framework to expose some valuable information from the host and the guest, and I think it's compatible with other works as well.
Yeah, makes a lot of sense. Thanks so much. Do you have any other questions? In that case, let's thank the speaker once again. And this concludes our session. And this was the last session of ASPLOS. Thank you so much for joining, and see you next year. Thank you so much. Thanks to all the speakers. Great job, everyone. And,